Everyone, and welcome to my today's video. So in our previous two videos we had discussed about unit 1, that was introduction to random variables, and the unit 2 was all about expectation moments and the different laws of large numbers. So today we are going to start off with our third unit, which is sampling and estimators. Right. So what is sampling and what is estimators? So let's discuss. So in statistics, we are often interested in understanding certain characteristics of a population, such as its mean, variance, or proportion. But in most real world scenarios, observing the entire population is not practical or possible. Instead, we collect data from a sample, a smaller manageable subset of the population. So, this leads to a fundamental question: how can we make informed guesses about the population based on sample data? The process of answering this question is known as statistical estimation. So, imagine you have a class of 52 students, and like currently you are there with five friends of yours, and immediately you have to submit the average score of your class in maths. Now it's not possible for you to go and collect all the marks कि आपके classmates को कितने मिले maths में. सो व्हाट यू डू इंस्टेड, आप अपने जो जिन फाइव फ्रेंड्स के साथ बैठे हुए हो, आप उनसे उन्हीं के मार्क्स पूछते हो बस. एंड इंस्टेड ऑफ टेकिंग द मीन, स्टैंडर्ड डेविएशन और वेरिएंस ऑफ द होल क्लास मार्क्स, you simply take mean, standard deviation, variance, etc. of the smaller sample. That is, आप पांच लोगों के sample बनाते हो and then you send the average कि yeah, this is the average. So in situations where you cannot make informed guesses about the whole population, instead you make it about a sample data, that is known as statistical estimation. So whole unit 3 is based on this topic only. Now why do we need estimation? Firstly, full data is rarely accessible. कि जैसे हमारे डेटा साइंस में वी हैव अ फंक्शन df data frame dot head. What does head do? Head gives us the first five rows, or yeah, head gives us the first five rows and tail gives us the last five rows. Why? Because the entire data set is often not visible on our single screen if it's too huge. For that, we need the head or tails function. Similarly, sometimes it's difficult to deal with huge data sets for which we just take a sample of it. Secondly, we need to make decisions under uncertainty. In real life applications such as quality control, public health, or economics, we must act based on partial information. अब क्लास के बच्चों के मार्क्स आपने जान भी लिए, इट्स गुड. What if you have to take a survey of all Indians or all people of your country on a certain medical issue? It's not possible कि आप सबके घर घर जाके information लो. And अगर आपने ले भी लिया, it's not some people might not be there, some might be on vacation, some might be on work. So it's technically not possible to always get the complete information. So we must learn how to base our decisions on certain samples. And thirdly, estimates guide future predictions and policies. Understanding key parameters helps in building models, forecasting, and making strategic decisions. Okay, so why do we need estimation? We need due to these reasons. Now, coming to what is an estimator. An estimator is a rule or formula that tells us how to calculate an estimate of a population from sample data. Okay, so an estimator can be anything: mean, then mode, etc. Okay, estimate is the actual number obtained from the sample, and estimator is the method to compute that number. Okay, it's like saying to compute. To compute means to evaluate something. Okay, and what is a computer? A computer is a device that helps us to compute. Similarly, estimate क्या है? Estimate वो number है जो हमें मिलता है by solving the sum. And what is the estimator? Estimator is the method or function used. Okay, then we have, like, for instance, the sample mean, that is 1 by n into sigma xi is an estimator of the population mean. कि imagine you have a population of 100 students. Out of that, you take the sample of 5 students and calculate the mean. Now, after some time, we'll study certain properties of this. So there I'll give certain more examples. So let's move on. So firstly, let's see an example how to estimate the population mean. So a random sample of 5 students has the following marks out of 10 students. So we have this. So use the sample mean to estimate the population mean. Given sample 67859, इसका mean is 7. So estimated population mean is also 7, कि जो बाकी के 5 बच्चे हैं उनके भी अगर मार्क्स हम इंक्लूड करके सबका मीन निकाले वो भी 7 होगा. दैट्स व्हाट वी एस्टिमेट. ओके. Estimating the population variance. So again, we have certain data, that is sample data. Now we have to estimate population variance using sample variance formula. So we use the required formula, that is S squared. S matlab standard deviation. The S squared equals to 1 by n minus 1. Sigma I equals to 1 to n xi minus x bar whole square. Now, why you use n minus 1 instead of n, that I had discussed in the unit 1 video. So if you haven't seen that yet, kindly go and check out that video. So after solving, we find out that the s squared is 2.5. So estimated population variance is 2.5. Okay. Now, what are the properties of an estimator? Now, let me tell you guys that the unit 3, of course, always has the maximum weightage. Okay. And mostly we are, subject to certain situations where the most unexpected things come. So, this chapter is a very, a very composed combination of both theory and numericals. So I'd suggest ki please be thorough with the theory concepts as well, because you never know, for 5 or 10 marks they can literally ask you a theory question also. Ki what describe the different properties of an estimator. So first property is what? First property is unbiasedness. In statistics, when we take a sample from a population, we often want to estimate some unknown quantity known such as the mean or variance of that population. The tool we use to do is called an estimator. So we know what an estimator is. Now what is unbiased estimator? What is unbiasedness? An estimator T is said to be unbiased for a parameter theta if E of T equals to theta. मतलब expectation of the estimator is equal to parameter. Okay. In simpler terms, an unbiased estimator does not symmetrically underestimate or overestimate the parameter. Okay. It's like saying unbiased, right? Unbiased का basic मतलब क्या है? Bias means there's some extra, factor added to it. Okay. And unbiased means what? It's the same. इसका मतलब ये basically है कि आपका sample जितना भी grow करते रहे, the overall mean or median does not change. A very simple example मैं आपको देता हूँ. If you take a simple, population 2 comma 2, इसका mean क्या होगा? 2 ही होगा. Another value you add 2 2 2, again same value of mean 2. You add 2 4 times 2 2 2 2, again the same mean 2. So this is a very basic example. So इसमें आप क्या, जितनी भी बार आप 2 ऐड करो, the mean value does not change, so it is kind of unbiased. Okay. So common examples of unbiased estimator: sample mean is an unbiased estimator of population mean. Now there might be proof asked for this, ki prove that the sample mean is an unbiased estimator of population mean. So that we'll be seeing in the upcoming examples. The corrected sample variance is an unbiased estimator of the population variance. Now why is corrected? Because it's usually 1 by n according to the mathematical formula, but now we take 1 by n minus 1. So for worked example, sample mean as an unbiased estimator. Sample of three numbers is taken, 5, 6, 7. Estimate the population mean. So sample mean हम पहले निकाल लेंगे, that is sum of the number by total number of observations. So it is 6. Now, suppose this was just one of many samples. In the long run, the expected value of x bar will be the true population mean, assuming each value is equally likely from the population. Thus, x bar is unbiased. Okay, मतलब x bar कितने भी grow क्यों ना करे, अल्टीमेटली उसका मीन 6 ही आएगा. ओके. Next, variance estimator with or without correction. So sample mean we find out 246 का it is 4. Now correct compute variance in two ways. एक है bias that is 1 by n which is according to the formula. So we find it 2.67 but with correction we find it as 4. So of course 4 and 4 is common when we take s squared equal to 1 by n minus 1, not 1 by n. So kindly remember this biased and unbiased thing for variance, because what most students do wrong is they take 1 by n, not 1 by n minus 1. So for estimation, the correct formula is s square equals to 1 by n minus 1 sigma xi minus x bar whole square. Okay. Bias check in a custom estimator. Suppose someone proposes the estimator t equals to 1 by n sigma xi plus 1 for estimating population mean mu. Is it unbiased? So we need to find if e of t equals to mu, because this is in this question we need to check if this estimator is unbiased for mu. So we have to always check if a is unbiased for b, then e of a must be equal to b. That we need to prove. So we take the expectation of this part, which ultimately comes out to be mu plus 1. But this is not equal to mu, this is greater than mu. So since et is not equal to mu, hence it is biased. Conclusion: the estimator overshoots the true mean by 1 unit. So it's not unbiased, okay? Now, why unbiasedness matters? Unbiased estimators are the gold standard because in the long run, they zero in on the true value of the parameter we are trying to estimate. Now, one other example is here: obtain the unbiased estimator of population mean from sample this. So we can take sample mean, which ultimately comes out to be new. Hence, x bar, that is sample mean, is an unbiased estimator of population mean new. So I have attached few questions for practice for unbiasedness. Unbiasedness is the most easy property of estimators. Okay, so please be very thorough with unbiasedness, because that's the literally easiest thing. Okay, like you, if you just get a question, let me show here. Expectation of, you need to show a is an unbiased estimator of b. So if you simply show this also, E of A equals to B, then also it's fine. You'll just do it. Okay, this is basically the entire notion of unbiasedness. But if it comes out to be B plus 1 or 2B after solving the sum, 2B, then it is not correct. Okay, then also it will be incorrect. That means it is estimator is biased. Okay, so that's all about unbiasedness of an estimator. Up next we have consistency. In estimation, consistency is a vital property that tells us whether an estimator becomes increasingly accurate as the sample size increases. Formally, an estimator Tn is said to be consistent if limit n tends to infinity, probability of Tn minus theta greater than epsilon is equal to 0. So does this look similar to Chebyshev's inequality? Yes, it does. So this means that as we collect more and more data, the probability that estimator deviates significantly from the true parameter theta becomes very small. Now इसका मतलब क्या है? Let me explain in basic terms, okay? Imagine आपने अपने क्लास के 5 बच्चों का वो मैथ्स मार्क्स का मीन लिया, एंड दैट मीन कम्स आउट टू बी 94. ओके, मतलब पांचों ही एकदम पढ़ाई में शातिर है. नाउ इफ यू इंक्रीज द सैंपल साइज टू 10, few mediocre students also are included. Now it the sample mean comes down to 80. Okay, अब 10 से now finally you take all the 52 students का mean. So what happens? 52 students का mean comes out to be overall 84. Okay, so neither 94 neither 80. Overall सारे students का mean is 84 out of 100. So what does this mean? This means कि as the like सैंपल साइज इंक्रीजेस, पहले 5 था फिर 10 हुआ, एक्यूरेसी बढ़ती जाती है. ओके, दैट्स व्हाई वी ऑलमोस्ट मस्ट सी दिस कंसिस्टेंसी थिंग. ओके, so why it matters? Unbiasedness ensures that we are on target on average, and consistency ensures eventually we'll hit the target more and more closely as n tends to infinity. Now, what are the key terms, key conditions for consistency? An estimated TN is usually consistent if it is asymptotically unbiased, that is, limit of n tends to infinity, E of Tn equals to theta, that is, expectation of the estimator is theta, and its variance tends to 0. So, mind you guys, एग्जाम में कोई क्वेश्चन रिलेटेड टू कंसिस्टेंसी आ गया, आप लोगों को बस ये दो प्रॉपर्टीज वेरीफाई करानी है. ओके, सो सैंपल मीन इज कंसिस्टेंट फॉर पॉपुलेशन मीन. So we can find out the formulas for sample mean and this variance. So as variance tends to zero, like sorry, as n tends to infinity, अब denominator अगर बहुत बड़ा हो गया तो overall fraction will like automatically become zero. Hence, xn is a consistent estimator of mu. That is, sample mean is a consistent estimator of population mean. Consistency of sample variance for population variance, then inconsistent estimator. Now this is also similar to the mean, okay, sample mean and population mean. So look, I just suggest you guys keep please do these small examples as we keep on proceeding. That will help you to clear the concepts. Okay, third example is inconsistent estimator. Let Tn equal to x1, that is only the first sample to estimate new. So expectation of Tn is new, unbiased, it's okay. But variance of Tn is sigma square because it's just one variable. Okay, so sigma square by 1 because n equal to 1. So sigma square. Now it does not shrink as n tends to infinity because there is no presence of n in the formula. So even though Tn is unbiased, it is not consistent. Is it clear? So conclusion, consistency tells us about long-term performance of an estimator. Comparing to estimators, so we have Z and Y and now we need to compare them. So check if Z and Y are unbiased estimators. So we check if E of Z equal to the mu, okay, but it is not equal to mu. It is 3 mu by 4, so Z is biased. But Y, E of Y is equal to mu, so Y is unbiased. Now we check consistency. For Z, the denominator grows slowly. Even though the numerator grows, the bias does not vanish, so Z is not consistent, okay. कहाँ था Z? What is Z? Yeah, so here what do we see? Denominator grows slowly, so even though the numerator grows, the bias does not vanish. So Z is not consistent. For Y, however, with proper normalization, if extended to large value of n, it behaves like a weighted average. Since it is unbiased and based on independent observation, hence Y is consistent. Compare variances. So we compare the variances of Z and Y. Now efficiency of Y over Z means var of Z by var of Y. So Y is unbiased and consistent, but Z is biased and inconsistent. Y is more efficient as well. Even though the variance is slightly higher, it gives the correct value on average and in the long run. Okay. So we have few questions for practice here. 7 and 31. Now we come down to the third property of estimators. What is it? It is efficiency of an estimator. What is efficiency? When we have two or more unbiased estimators for the same population parameter, we prefer the one with least variance. This idea leads us to the concept of efficiency. Okay. So मतलब क्या है? मतलब है कि अगर आपके पास तीन वेरिएबल्स है टी एस आर और तीनों की वेरिएंस है V1, V2, V3, जिसमें V1 is smaller than V2 and V2 is smaller than V3. So जिसकी वेरिएंस सबसे कम होगी, that is T, So T is the most efficient estimator of the given population parameter, and it is also called the minimum variance unbiased estimator, that is MVUE. Is it clear? So लाइक आपको अगर जितने भी वेरिएबल्स एन वेरिएबल्स दी हो कि जैसे T1, T2, T3, तीनों की वेरिएंस ऐसी आई 2.4, then 3.6 and 1.2. Then T3 is the most efficient estimator, as well as it is the MV UE of the given thing. Hope it's clear. What's a minimum variance unbiased estimator? Because T3 का सबसे low variance था. Okay. So comparing two simple estimators T1 and T2. Now T variance of T1 is sigma square by 2. Variance of T2 is 5 sigma square by 8. So efficiency of T1 with respect to T2 is 1.25. So T1 is more efficient. Efficiency अगर 1 से greater हो, so we can say that the first estimator is more efficient than the second. Simple sample mean versus weighted estimator. Okay, so simple sample mean क्या होगा 1 2 3 by 3, simple sum of three things by 3. T2 क्या है x1 plus 2x2 by 3. Okay, so after solving the sum, and one more important thing, we of मतलब by default कोई भी चीज का expectation we always take it as new. Okay, so both are unbiased. We can see that because expectation of x1 is mu, 2 into mu, so it's ultimately 3 mu by 3, which is also mu. So variance of T1 is however sigma square by 3, and it is 5 sigma square by 9. So ultimately it's 5 by 3. Again T1 is more efficient. Two estimators with given variances. So suppose two unbiased estimators have variances 4 and 5. Find efficiency with respect to T2. So with respect to T2 का मतलब क्या है? T2 ऊपर रहेगा, T1 नीचे रहेगा. फाइन. लाइक बहुत बच्चे कंफ्यूज हो जाते हैं कि विथ रेस्पेक्ट टू टी टू है मतलब टी टू को डिनोमिनेटर पे होना चाहिए, बट इन हियर इट इज ऑपोजिट. जिसके रेस्पेक्ट में होगा वो ऊपर रहता है. सो यू कैन जस्ट इमेजिन और रिमेंबर इट लाइक दिस कि रेस्पेक्ट जिसे हम देते हैं वो हमेशा ऊपर रहते हैं. ओके, लाइक स्टेटस वाइज और however we often give respects or pay respect to the people who are above us in any field. So T1 with respect to T2 means T2 by T1. So it comes out to be 1.25. So T1 is 25% more efficient than T2. So अब तक हमने क्या पढ़ा है? Estimator and these three properties of estimator: unbiasedness, consistency, and efficiency. Unbiasedness ensures that we are hitting the bullseye on average. Consistency ensures we are eventually hit close to the bullseye as the sample size increases. And efficiency ensures we hit the bullseye with minimum scatter. Okay. So another sum I have given here, you can check it. It's related to efficiency and MVUE. Okay. So now the next topic we'll get is, yeah, I have attached few questions for practice here as well. Let's go through them. Now we come to the fourth property, that is sufficiency and completeness of an estimator. What is sufficiency? Now, in the world of statistics, we often seek to find statistics that give us all relevant information. Two essential concepts in this regard are sufficiency and completeness. What is sufficiency? A statistic Tx is said to be sufficient for parameter theta if it captures all relevant information about theta that is present in the data. Okay. So अब sufficiency का basic मतलब क्या है? When are you said to have sufficient knowledge for the exam you're about to sit in? Okay, you're said to have sufficient knowledge जब you feel that okay, I can, I think I can score 95 to 100% marks. But again, yeah, sufficiency changes according to people. जिन्हें बस पास होना हो उनके लिए 40% का प्रिपरेशन सफिशिएंट है. ओके, जिन्हें अच्छा करना हो उनके लिए 80 to 90 है, वॉट एवर अकॉर्डिंग टू दैट पर्टिकुलर माइंडसेट ऑफ द पर्सन. So it's nothing is good or bad or nothing to judge. It's according to everybody's own perception. So the formal definition of sufficiency is given by the factorization theorem. According to this theorem, a statistic Tx is sufficient for theta if PDF can be written as Fx equal to g of Tx comma theta into h of x. इसका मतलब क्या है? सो देखिए, अगर हमें ऐसा कोई दिया रहे कि जस्ट अ सेकेंड, 2x then 2x plus 3, sorry, not 3, just a moment, 2x plus 4x square plus 6x cube plus dot 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 plus you know uh 2n x to the power n. दिस इज अ सीरीज. ओके, अब इसमें अगर हम लाइक we factor them, we can basically, like, this is just an example. This can be factored into two parts. Okay, we can multiply two parts. One is terms containing x and one is the terms containing just the number. Example, 2 plus 4 plus 6 plus 8 plus dot dot dot. Okay, so this is a basic notion कि we can segregate this both. Okay, so one thing, for example, you are having kheer. Okay, now many people have allergies in dry fruits or sometimes raisins, kishmish. What they do, they segregate the raisins from the kheer or whatever dish you're having. You're having a pizza. Some people have problems with jalapeno or whatever. They segregate those particular items. They don't throw away the whole dish. Similarly, you also divide fx into one term containing theta and another term independent of theta. Okay, so here g of tx comma theta depends on the data only through the test statistic and the parameter, whereas hs is a function of the data x alone. It does not depend on theta. So please, remember this particular condition of sufficiency. And what is completeness? A statistic is said to be complete if no non-zero function of the statistic has an expected value of 0 except the zero function itself. Okay, formally tx is complete for any function ht if e of ht equals to 0 for all theta. It implies h of t equal to 0. So this property ensures that statistic does not miss any valuable information about theta. So a statistic is said to be complete if no function of the statistic has an expected value of 0. Okay. For example, if t is a estimator and e of t is anything, literally anything except 0, like it's 2x, it's n square, e of t is new, anything but not 0, it's said to be complete. Fine. आपको बस ये इंश्योर करना है या प्रूव करना है कि इसका ex is not equal to 0. So why does this matter? Sufficiency helps us to reduce data to its essential parts. It's like abstraction from object oriented programming, and completeness ensures that the statistics tx is as informative as possible, because expectation ही अगर 0 हो गया, then आप how will you explore further? Okay, it's much like real life only. Okay. For example, if we don't have any expectation from something at all, how do we get the motivation of continuing? There's no motivation. Similarly, हम expectation को भी zero नहीं कर सकते. Okay, and the Lemans-Keff theorem, if a statistic is both sufficient and complete, it is often the best unbiased estimator for theta. Okay, now this is not a part of your curriculum, but in general, this is a theorem. If it's both complete and sufficient, it is the best unbiased estimator for theta. Okay. Okay, so now we have few examples. So sufficiency of the sample mean for normal distribution. So first we write down the likelihood function for this data, that is f equals to this. So for the sum of the sample values is sufficient for mu, since sample mean is equal to this, contains all information about mu. Okay. Hence Tx is a sufficient statistic for nu. Why? Because sample mean is already containing all the information about population mean, right? We have a term for the sample mean this side. So it already contains all the necessary information for the population mean. Hence, Tx, that is the estimator, is a sufficient statistic for nu, that is population mean. Completeness of exponential distribution. So we have this exponential distribution, lambda e to the power minus lambda x. So consider the statistic t equal to this, which is the sum of the sample values. We want to show that Tx is complete for lambda. So to show this, consider any function e of ht equals to integration from 0 to infinity h of t dt. For completeness, we need to show that if e of ht equal to 0 for all lambda, then h of t equal to 0. In this case, t of x is a complete statistic for lambda. Okay, so if we can show that this integration ka answer is 0, then we can be able to prove that h of t is 0, that is the entire thing is complete for lambda. So in this case, t of x equal to summation of xi is a complete statistic for lambda. Okay. Now sufficient and complete statistic for Bernoulli distribution. So Bernoulli distribution ka likelihood function we write here. Here the statistic Tx is both sufficient and complete for P, because the sum contains all the information about P and there is no other non-zero function of this statistic that would have expected value of 0 for all P. So basically, guys, I just say that these parts are very theoretic, okay? Like there's nothing much to understand. You are just supposed to write this all the way it's written. So you just note how structured the things are, okay? You note the structure of the answers or solutions, and at least you frame the answers properly. So sufficiency tells us that once we know the statistic Tx, we have all relevant information about the parameter theta. Completeness ensures that no additional non-zero function of the statistic can provide more information about theta. And if a statistic is both sufficient and complete, it becomes a powerful tool for estimating parameters and is often the best unbiased estimator. So few questions for practice I've given here. You can practice. Now, what is the maximum likelihood estimator? Okay. Maximum likelihood estimation approach. When we observe a sample and want to estimate an unknown parameter theta, a powerful and commonly used method is MLE, or maximum likelihood estimation. This method is rooted in a very intuitive idea. Choose the value of theta that makes the observed data most probable under the assumed model. So आपको अगर I ask right now कि without thinking anything, tell me what can be the highest marks obtained in your class. So you'd say it's 100, right? 100 out of 100. So what is maximum likelihood estimation? Given a sample drawn from a distribution with PDF or PMF FX, the maximum likelihood function, or the likelihood function, is L of theta equals to pi I equals to 1 to n f of x comma theta. Now basically what is this pi? Sigma, you all know, sigma of xi means sigma summation of x naught to xn. Okay, if I write I equals to 1 to n, it means sum from x naught, sorry, x1 to xn, right? xn. This is denoted by this. So similarly, pi represents product. If I say pi from I equal to 1 to n xi, it means x1 into x2 into x3 until xn, x1 into x2 into x3 until xn. So this is the basic notion of pi, and the likelihood function is given by the product of all the PDF points. Okay, so this function gives us a measure of how likely the observed data is for different values of theta. So the key intuition behind MLE. Suppose you have you have a model and some data. So among all the possible parameter values, which one makes your data the most likely? Okay, MLE gives you that value. It does not assume prior information. It just uses the observed data and tries to explain its best. So key properties of MLE: consistency, asymptotic normality, asymptotic efficiency and not necessarily unbiased. सो अभी हम एक सम करते हैं तो आप समझ जाओगे एमएलई में करना क्या होता है। एमएलई मैक्सिमम लाइक्लीहुड एस्टिमेटर फॉर द पैरामीटर पी इन अ बर्नौली डिस्ट्रीब्यूशन। लाइक्लीहुड फंक्शन पहले लिख लो। लाइक्लीहुड फंक्शन इज नथिंग, जस्ट एफ एक्स के पहले आपको ये लिखना है पाई फ्रॉम 1 टू एन, पाई आई इक्वल टू 1 टू एन। अब आपको बोथ साइड्स में लॉगरिथम लेना है बिकॉज इससे कंप्यूट करना इज नॉट इजी। फॉर सिंप्लीफाइंग दिस एक्सप्रेशन वी टेक log on both sides. This is known as log likelihood. Now we differentiate DDP of log LP, differentiating both sides and setting right side to 0. Then we find the value of P, which ultimately comes out to be X bar. So the MLE of P is the sample mean. So maximum likelihood estimator for P in Bernoulli distribution is nothing but the sample mean. MLE for lambda in exponential distribution, fx equal to lambda e to the power minus lambda x. तो likelihood हम निकाल लेंगे pi I equal to 1 to n, then the given PDF. So we find out the given expression, then log likelihood, we take log both sides and differentiate. So please remember these four steps. This will help you conquer any MLE question. MLE as such looks very lengthy and tedious, but the key thing is only have to follow these four processes. Okay. MLE of lambda is the reciprocal of the sample mean. Is it clear? Next, MLE for mu in a normal distribution with known variance. So let x1, x2, xn be like normally distributed with mean mu and variance sigma square with variance known. PDF is this, log likelihood is this, then maximizing this is equivalent to minimizing this. Okay. Why? Because it's in negative. So it ultimately gives mu cap equals to x bar. So again, the MLE of mu is population mean is nothing but the sample mean. Conclusion: MLE is a method of estimating unknown parameters by maximizing the likelihood function. It's based on the simple idea: choose the parameter that makes the observed data most probable. MLE often leads to natural estimators like sample mean, but it always doesn't give unbiased estimates. Understanding how to derive MLEs builds strong statistical intuition and prepares you for deeper inference methods. So this overall topic itself is so tedious. I have been going through this that now I'm not even able to pronounce it properly. Intuition. Anyways, up next we have few questions for practice. You are requested to go through these themselves, and I have attached the solutions in the Google Drive link, which is there in the description of the video. What is MME? So MLE we did. MME, method of moments, is another classical way to estimate unknown parameters for a distribution. It is especially useful when the MLE is difficult to compute or doesn't exist. So MLE में हमने देखा कि we have to take log, then do many other steps. So sometimes log is not computable for complex functions. For them हम क्या करते हैं? MOM, that is method, sorry, MME, that is method of moments, we compute. Idea behind the MME is simple. We know that a distribution has certain theoretical moments like mean, variance, etc., that depend on unknown parameters. We also have sample moments calculated from observed data. So we match the two and solve for the parameters. Moments is something which we have learned in second unit. So we know, right, that mgx, say we can find out mx1, mx2, everything. General process: compute the first few moments from the sample, example sample mean and variance. Write the corresponding theoretical moments in terms of the unknown parameters. Equate sample moments to theoretical moments, and finally solve the resulting equation to find the estimates. Why it works: if the mean of distribution is g theta and sample mean is x bar, we equate g theta equals to x bar, then we solve for theta. Example, if this is theta plus 1, then theta equals to x bar minus 1. For two parameters theta 1 and theta 2, we equate this, because that way we have to get the first two moments, then solve the system of equations. Okay. Example, mme of lambda in exponential distribution. Suppose x1, x2, xn are belonging to exponential distribution with parameter lambda, where ex equal to 1 by lambda. Using the first moment, we can get lambda equals to 1 by x bar. So 1 by x bar is the mme of lambda. Okay. mme for A in uniform distribution from 0 and A. So sample mean is x bar and theoretical mean is A by 2. So we can get a cap equals to 2x. So the method of moments estimator for A is twice the sample mean. So that way we can find the conclusion. Moment method of moments is straightforward and only requires basic algebra. It is especially useful when MLE is messy or not very defined. However, MME may be less efficient than MLE and may produce estimates outside the valid parameter ranges. This is one drawback for MME we must remember. 2 mark question में आ सकता है, state one case when MME is less efficient than MLE. So given data x1, y1, x2, y2, xn, yn, assume that y1 is n from b0 plus b1 xy, comma sigma square. That is, this is the mean and this is the variance independently for I equals to 1 to n, and that variance is known. Show that MLE of b0 and b1 must be the same as LSE of these parameters. So write the likelihood function, we write the joint likelihood function. Okay. Take the log likelihood, we take the log likelihood of this function. Maximize the log likelihood. So since sigma squared is known and constant, maximizing log L is equivalent to minimizing the sum. Okay. But this is exactly the objective in LSC. We take the partial derivatives of S with respect to B0 and B1. Okay, because as like you see what happens, we partially differentiate with respect to b0 and b1 and then equate them both to 0. Then using the first equation we get b0 equal to y bar minus b1 x bar. Plugging into the second equation we get this. So technically this is a bit lengthy and tedious sum, but this is a basic sum related to linear regression. Okay. So finally, we get these equations that B1 equals to sigma xi minus x bar into yi minus y bar divided by sigma of xi minus x bar whole square, and beta naught equals to y minus beta 1 x bar. Okay. So final result, the MLEs, which are the same as LSEs of B0 and B1, are B1 equal to this and B0 equal to this. So what are the steps we followed? Firstly, we formulated the joint likelihood function. We took log likelihood, maximized the log likelihood. Then we differentiated with respect to B0 first and B1 and then equated them both to 0. Then we defined x bar and y bar as the sample means of x and y. Then using first equation, we found the value of b naught. Then we found the value of b1, beta 1. Then finally, we derived the final values for beta 1 and beta naught. So here are a few more questions of practice for MMEs, that is method of moments. So with this, we come to the end of unit 3. Here we learned about estimators, their properties, that is unbiasedness, consistency, sufficiency, efficiency, completeness. Then we came to learn about maximum likelihood estimation and method of moments estimation. Okay, so these are all the topics which you need to remember for unit 3, that is some sampling and estimation. So I have given a summary of the third unit: method, unbiased estimation, consistency, efficiency, sufficiency, completeness, MLE and MME. Here are the formulas. Unbiasedness के लिए you have to prove E of t equal to theta. Consistency के लिए t of n tends to theta as n tends to infinity. Efficiency is variance of t2 by t1 with respect to t2. Okay. Sufficiency factorization is this, आपको थीटा को अलग करना है देन एच एक्स. MLE is the maximize log likelihood. You have to likelihood function is product of all the PDFs. Method of moments is match sample means to theoretical means. So this last sheet is a very good for a concise revision, okay, of unit 3. So with this, we come to the end of unit 3, sampling and estimators. I hope this is clear to you all. So, just a moment. So, if we want to revisit once from the beginning, um, Unit 1 may we studied about random variables. Just a moment. Yeah. So basic probability rules, conditional probability, Bayes theorem, random variables, expectation variance, standard deviation, covariance and correlation we studied. Then joint distributions, marginal and conditional probability, continuous joint distribution, applied probability, and correlation in practice. Fine. Then we had unit 2, that is expectation and moments. So there we studied, just a moment, iska summary. Here, formula sheet, unit 2, we had transformation of random variables, univariate transformation, and multivariate transformation. Then we studied MGF, that is moment generating function. Then we studied Chebyshev's inequality. Then law of large numbers, central limit theorem, joint PMF PDF marginal distributions, as well as independence. Finally, conditional distributions and expectation, and discrete and continuous distributions, PMF, PDF, and MGF table. So this entire table I have provided here for your enhanced revision. So in case in exam you're not also able to solve, at least you can write the final answer. Okay. Then today we studied about unit 3. Let's see, just a moment. 80. So today we studied about unbiased estimators, consistency, efficiency, sufficiency, MLE, likelihood function, and method of movements. Okay. Now few topics from syllabus, not for evaluation purposes, but just for theoretical understanding. ओके लाइक आपके सिलेबस ऑफ यूनिट 3 में कुछ टॉपिक्स मेंशन थी जो लाइक ऑफिशियली दोज आर नॉट अ पार्ट ऑफ योर सिलेबस एनीमोर, बट स्टिल since there is a record of questions coming from anywhere, so it's better to at least have an idea. Sampling and its types. Sampling क्या होता है? We collecting a group of data from a population. Okay, that is known as sampling. So sampling helps us to create samples. A good sample represents the population accurately. इस मतलब जैसे 100 स्टूडेंट्स की एक क्लास है, if you just take a sample of 5 good students or 5 meritorious students, that won't help us to मतलब estimate properly, or 5 weak students, that won't help us to estimate properly. You must take a unbiased thing. Types of sampling: random sampling, every unit in the population have equal chance of getting selected. Stratified sampling, we divide the population into groups and then sample proportionally from each group. Systematic sampling, choosing every kth item from a list. अगर 100 बच्चे, you choose every 10th item from 10th student from the class. Clustered sampling, divide population into clusters and then randomly select some entire clusters. Convenience sampling, choose whoever is easiest to reach. First benchers को choose कर लो बस. It is very biased, okay? And the last topic, algorithms using regression. So gradient descent algorithm, it's a numerical optimization technique used to minimize a cost or error function. ओके, कि जैसे ग्रेडियंट जैसे जैसे इसका बढ़ते जाता है, द एरर सीम्स टू रिड्यूस. ओके. लोकली वेटेड रिग्रेशन, a non-parametric version of linear regression. इसमें instead of fitting one global line, LWR fits a separate regression at each query point, giving more weight to nearby points. So instead of a straight line, we see a group of points. Okay. So the weights of every regression point gives us a better idea about LWR. Logistic regression, a classification algorithm that uses a logistic or sigmoid function used for predicting binary outcomes like yes, no, pass, fail, or spam, not spam. Key feature predicts probabilities between 0 and 1. Formula is this. Okay, logistic regression. So this was all about even the extra topics of Unit 3 I've covered, which were there in syllabus officially, but not a part of your exam. Sampling and its types, and algorithms using regression. So with this, I'd like to conclude my today's video. I'd like to wish all of you best of luck for your exam. Do very well. And in case of any doubts, you can simply reach out to me regarding this PDF. The link is shared in the YouTube description of this video. You can open the file and practice whatever sums you like, and you can even verify the answers. Okay. Thank you so much. Goodbye. Have stay well. Thank you.